Okay, so welcome back, everybody. Yesterday we left off at this question of isomorphism, so I'm just going to bring that back onto the screen right now. So this was the last thing we talked about yesterday, which is the notion of two graphs being isomorphic. So said they are isomorphic to one another if there exists a one-to-one correspondence F, going from the vertex set of G to the vertex set of H, such that for each pair of vertices in the vertex set of G, this edge, xy, is in the edge set of G if and only if the image of the two vertices, that edge, is in the edge set of H. So I even said it when I wrote it, that intuitively, what does this mean? This isomorphism F, so such an F is a map. When I say map here, like in most math courses, like if I say map in a topology course, maybe I mean a continuous function. But I'm using map here to refer to just a general function. So when I say map, I mean function. I'll use those interchangeably. So I don't mean anything special by this, just function. It's just easier to say map than function. Such an F is a map from the vertex set of G to the vertex set of H that preserves adjacency. That's another way of thinking about it. So it is likely, this is not your first, well, not just likely, it's guaranteed. It might not have been stressed an awful lot in your linear algebra course, but depending on who you had as an instructor. But isomorphism is a thing that you have seen before. Isomorphism, right, from the Greek, iso, same, morph, type. Same type. That's what an isomorphism, or two objects that are isomorphic, are. They are of the same type. And as we saw yesterday, this is basically saying that if two graphs were isomorphic, they were essentially relabelings of one another. And we're going to see further examples of that here in a second. But the reason why this is, I'm going to zoom out from graph theory for a second. Whenever you encounter an isomorphism in math, this notion of objects or mathematical structures being the same or the same type, isomorphic, the idea is that there is some structure that is being preserved by the map. So, and you can type in chat the other places you've heard isomorphism other than linear algebra. So you can talk about isomorphisms between groups, for instance. What is it that's being preserved in each case? In each case, the structure in question is being preserved, or the essential part of the structure is being preserved. So, for instance, in a vector space, what is an isomorphism preserving? You can type in chat if you remember what it is that an isomorphism is preserving, because you might say, well, the most important part of the isomorphism is that it's a one-to-one correspondence, right? Meaning it's one-to-one and on-to, so it's somehow keeping the count the same. That is a consequence that is true and that is needed, but that's not really the only thing. The big thing here is that it preserves adjacency. It's this requirement here. In a vector space, what was the analog of that requirement? Does anyone know or remember? What object is being preserved in a vector space isomorphism? Well, it's linear combinations. So what is being preserved by a vector space isomorphism is that it is in fact a linear map, which means it respects linear combinations. Linear combinations being like the fundamental building block of any vector space. So the thing being preserved in a vector space isomorphism. So a vector space isomorphism is a one-to-one correspondence between vector spaces that preserves linear combinations. That's it. The reason I'm stressing this, I know this is not a linear algebra course necessarily, although you're going to see today where you're going to be able to bring some of that to bear in graph theory. But the reason I'm stressing this is so that when you encounter this in other contexts, you're going to say, yeah, okay, I see. I see what's going on here. An isomorphism is a one-to-one correspondence that preserves the structure that I'm worried about in this context. So in this case, it means that the graphs are essentially relabelings of one another. Okay, and so let's look at this example that we saw yesterday. So in this example, we had two graphs. I asked, were these the same? And the answer is yes, these are isomorphic. So I'll mention very briefly, like, whether are we abusing terminology here when we say these are the same because they are isomorphic. We're not going to make a distinction there, and the reason why is because what we mean by they are the same, you might have a philosophical objection and say clearly they're not the same. This one sits here and this one sits here. How could they be the same? There's that one, there's that one. They can't be the same. But they are the same graph, right? As graphs, they are the same. So if the only thing you are referring to here is their graph structure, that graph structure is the same for both of these. These are just visual representations of the same graph, right? Maybe if you're a Platonist, you say, well, the actual graph here being represented by both of these exists in the world of forms, and it exists in some immaterial, eternal, perfect world of forms, and these are just the visual representations of the same object, right? If you want to go that route. Anyway, nevertheless, these are the same as graphs. So if they're the same as graphs, that means there should be an isomorphism between them. There's not that many vertices here, right? There's only 8. So that's only 8 points that I need to define a function on, and I want to do that. So I gave a suggestion yesterday where if you took C and moved it out here, and the edges stretched as they needed to as you move C. So you take C, move it out here, take D, move it out here, take E, move it out here, take F, move it out here, so that you get a picture that looks like this, and then that suggests where each vertex should go. So this visual moving of things, right? Remember in a graph, what's important is the vertex, the vertices, the edges, and then the adjacency. So as long as that's preserved, I can stretch these things as I need to, right? They don't need to look exactly like this. It doesn't need to be in an octagon shape. It doesn't need to look like this either. It can look however, as long as I haven't altered the adjacency properties of these existing vertices and edges. So when I do this, this is actually suggesting to me the isomorphism that I should do. So I should send A to 1, B to 2, C to 8, D to 3, E to 7, F to 4, G to 6, and H to 5. So if I was going to actually, in that example, if I was going to, so this is for my example here, if I define, F of A to be 1, F of B to be 2, F of C to be, what did we say, 8, F of D to be 3, I think we said, F of E to be 7, F of F, well, this is kind of bad notation, but whatever, 4, F of, maybe I should have used phi instead of F, F of G to be 6, and F of H to be 5. Then a way of thinking about this isomorphism, right, is the isomorphism is the relabeling function, right? It is the thing that tells you how to relabel the vertices in such a way that it becomes clear they are the same graph. Okay, that's another way of thinking about this. This is actually another way of thinking about isomorphisms, period, even in other contexts. But here it's especially nice just because the graphs in question in these examples tend to be small and they're just finite sets, right? It might be a little bit stranger. You're talking about an isomorphism between like continuous objects, right? That might, having that thought of as a relabeling function might seem a little bit stranger, but here it's a little bit more natural. And so, as I said, we are going to say, so in this course, if graphs G and H are isomorphic, we will say they are the same graph, or simply that G is H. Of course, because this is a one-to-one correspondence, all of this is invertible. So, as I mentioned yesterday, if G is isomorphic to H, H is isomorphic to G. So there's not a direction to this. This works in both directions. The reason, of course, why this is so important, and the reason why the notion of isomorphism is always important in this way is if you are working on a problem involving a graph, and I come to you with another problem involving another graph, right? It is nice to be able to know whether the graphs we are talking about are actually distinct, different graphs, or whether they are in fact the same graph, right? Like when you are looking at something, and in another context, right? You have a graph in front of you arising from some situation you're interested in. You might want to know if you have encountered this specific graph before, right? In which case, any other work you've done on that graph, you would already know, right? So obviously it's nice to be able to know whether you are dealing with the same graph or a different graph. So some facts about isomorphic graphs. I mean, these facts will strike you. First of all, this comes directly from the definition, and you will be using this in your homework that'll be posted later today. Some of these, of course, are going to be very obvious if you intuitively understand that isomorphic graphs are the same graph. If I'm calling them the same graph, then there are some things that absolutely had better line up, right? So, fact one, if G and H are isomorphic, maybe I'll do this so that I don't have to rewrite this phrase in every single one of these lines. So if G and H are isomorphic, then firstly, their vertex sets and edge sets have to have the same count, right? They have to have the same cardinality. So the cardinality of the vertex set of G must be the cardinality of the vertex set of H, and the edge sets have to be the same. This is obvious if we are calling these the same graphs, right? Then of course they have to have the same number of vertices and the same number of edges. But why does this follow? Where does this fact come from? This doesn't need much of a proof. This is right out of the definition. It's because an isomorphism is necessarily a one-to-one correspondence. So it's one-to-one and onto. And just as a set theory matter, what that means is that the cardinalities have to agree. Okay? So the cardinalities match up. I mean, especially for finite sets, it's very easy to say this. We don't even have to get into trickier questions about cardinality and countability and things like that because we're not dealing with infinite sets. So that's the first fact. Second fact. Well, the degree sequences have to be the same. So if I label, if I choose, say, descending order for the degree sequences of G and H, those must be the same. These two facts, of course, give you a very easy way of saying whether or not some graphs are isomorphic. If you have two graphs and one of them has more vertices or more edges, they're clearly not isomorphic. If you have two graphs and the degree sequences, once you've written them out, differ at all, then they can't be isomorphic. Okay, for the same reason. Degree sequences having to be the same. Where does this come from? This doesn't come from the one-to-one correspondence. This comes from the fact that F preserves, an isomorphism F preserves adjacency, right? So these degree sequences are not allowed to change. If the degree sequence changed at all, that would not be preserving adjacency, right? Something would have happened there to alter it. Okay. And then one more. Their complements must also be isomorphic. Okay. So these are some quick facts. 1 and 2 are kind of immediate from the definition. 3 might have you prove this one as a homework exercise. So this is going to be part of your homework. These two are pretty much immediate from the definition. But here's a warning here, right? So here's warning. The converse of facts 1 and 2, or I should say the converses of 1 and 2 are not true. What do I mean? I mean that the converse statements of, well, if G and H are isomorphic, then they have the same vertex and edge counts. And if G and H are isomorphic, the degree sequences of G and H must be the same. The converse statements are, if two graphs G and H have the same vertex and edge count, they are isomorphic. That's false. And if the degree sequences of two graphs match up, they're isomorphic. That's also false. So I'm going to give you a counterexample to both of those right now. So here is an example. Let's consider the cycle on 6 vertices. So what does that look like from our special graphs? You know, an easy way of depicting this visually is like this. Okay. Now let's also consider the following graph of order 6. It looks like this. These two graphs, let's label them G and H. So here's G, here's H. These two graphs satisfy the vertex set of G is equal to the vertex set of H. We could even use the same letters to label them if we want. The edge set of G is equal to the edge set of H. And their degree sequences are the same. Well, what are the degree sequences? Let's label them out. We'll start at this vertex and we'll go counterclockwise. Okay. So 2, 2, and then of course we could rearrange them if we needed to, but I've looked ahead and I know that I'm not going to have to rearrange them, right? 2, 2, 2, 2, 2, 2. Okay. Every vertex is degree 2. Oh, but that's also true here. So you're simultaneously seeing something else, right? What do you notice about G and H in terms of connectivity that we discussed yesterday? Well, G is connected, H is not, right? G has one connected component, just G itself. H has two connected components. But notice the degree sequences are exactly the same. So clearly the degree sequences alone are not at all enough info to tell you whether or not a graph is connected, right? Because both of these have the same degree sequence, but one is connected and one's not. That might be obvious to you that would be the case, but still it's nice to see this. So these two graphs satisfy. They have the same number of vertices, same number of edges, and their degree sequences are the same. Are identical. But they are not isomorphic. How do you know they're not isomorphic? There's a few things you could say here. Okay, there are a few things that you could say to distinguish these as being non-isomorphic. I want you to think about it. One thing you might ask yourself immediately is, does isomorphism necessarily preserve connectedness? Right? So if two graphs are isomorphic, if one of them is connected, does the other have to be connected? It seems like that would be needed. It seems like that would be required. And yet, G and H here, one is connected and one isn't. So that would be one way of saying something. Think about why those are not isomorphic. Try to construct an isomorphism between them that preserves adjacency in the way it should. There's only 6 vertices here, right? So not a whole lot of options, not a whole lot of choices. Think about this, but this is a word of caution here. Okay, that it is not enough for two graphs to share the same number of vertices, same number of edges. It's not enough for them to share the same degree sequences. But on the other hand, the question of whether two graphs are isomorphic obviously is going to be easier to answer in a situation where these differ, right? So if they have different vertices, different number of vertices, different number of edges, clearly they're not isomorphic. That's going to be very easy to detect. So that's not going to be a problem. If the degree sequences differ, again, that's going to be easy to detect. That's also not a problem. And so primarily, right, you're going to be like, you would be spending the most time on situations where both of these were the case. You're dealing with two graphs that have the same vertex and edge count and the same degree sequences, and you're asking whether or not they are isomorphic. Now, the big warning here that I mentioned briefly yesterday, which is, well, how hard is this problem in general? So another warning. The question of determining whether two graphs are isomorphic is difficult. This is not something that is very easy in general. This is easier if the graphs are small. or obviously have different vertex or edge counts or different degree sequences. So obviously, if they have different vertex edge counts, you can detect that. That's easy. If they have different degree sequences, that's easy. If the graphs are small, then there's again like it is easier to see whether or not they are isomorphic. But once a once the graphs involved have vertex count that's large enough, this becomes a very hard problem. In complete generality. So there are some other strategies here. So what are the other strategies maybe? Let's say they have the same vertex edge count, they have the same degree sequences. What are some strategies that you might use? You might remember that in fact 3, what had to be true if they were going to be isomorphic was their complements needed to be isomorphic. So you could compare complements. So you could compare complements, right? If the complements are not, maybe the complements are easier to deal with, right? Than the graphs themselves. And if the complements are not isomorphic, then the graphs would not be isomorphic. And the question is, if the complements are isomorphic, are the graphs necessarily isomorphic? Notice I did not include the converse of fact 3 as a problem. So maybe that's a thing that you could think about. The hint here is what's the complement of a graph? Okay. All right. So what are some strategies? Compare complements. Compare subgraphs. What do I mean by that? If two graphs are going to be isomorphic, then the subgraphs they contain should also be identical. Okay, so if one of them contains a subgraph that the other one does not, that's a problem. Okay, so compare complements, subgraphs. You could compare degrees of adjacent pairs of vertices. Instead of the entire degree sequence itself, which is just the degrees of each vertex taken, listed in, say, descending order, compare degrees of adjacent pairs of vertices. These are some strategies. This is not exhaustive. There are different things. There are some higher order things that can be done here. Again, we have reference to like connectivity. That requires a little bit more sophistication to talk precisely about those things, which we'll do. We'll do all that. But here's some strategies to get you going for figuring out whether or not graphs are isomorphic. You're going to have to do this in your upcoming homework. So look forward to the homework. Homework problems on this will help. It will help give you an idea of how this works. Okay, so that is that for now about isomorphic graphs. But now we have a notion of graphs being the same. So we can very precisely say in which sense two given graphs are the same or represent the same graph. And like I said, we are going to just say those graphs are each other, essentially. So we would say G is H. Maybe instead of every single time saying G is isomorphic to H. Okay, so now we move on to the notion of distance in graphs. Our idea is to put a distance function on a graph G. Oh, I already said A. But hey, guess what? You have likely already seen what a distance function is. Someone in the chat tell me what's another name for a distance function. While I start writing what we want our distance function to satisfy. We want this distance function to be a this word. Okay. So we want the distance function to be this, and this is a thing that satisfies the following. So if our distance function, I'll write it as d here, where this is understood to be the distance between 2 points or 2 vertices in the case of a graph. We want it to satisfy 3 things. So 1, we want it to satisfy that the distance between 2 points is always non-negative for any 2 points. And if it is 0, this only happens if the 2 points are in fact the same point. Does anyone remember what this is called? Second thing we want this distance to satisfy. The distance from x to y should be the same as the distance from y to x. That is how distance works in our world as we understand it, right? The distance from New York to LA should be the same as the distance from LA to New York. Shouldn't matter what direction I'm talking about here. If we're just talking about the distance between those things, it should be the same. What's that called? And lastly, the distance between x and y should always be less than or equal to the distance between x, some other point, plus the distance between that other point and y. So it should always be closer to go directly from x to y rather than going from x to z and then from z to y. What's that called? What is this? What did I just write? This distance function, of course, is a metric. Any set that possesses this sort of function satisfying these 3 properties, which I'll name here in a second, is called a metric space. Okay, we can talk about a metric space. So that is, we are turning our graph into a metric space by putting a metric on it. What is this first property called? This is called positive definiteness. This is saying the metric is positive definite, so this is positive definiteness of the metric. This is called symmetry. So this is symmetric property or symmetry. And this is called the triangle inequality. So those 3 things, those are the 3 properties that a metric must satisfy. And all this is saying is that the function d that I've defined in this way, satisfying these properties, it behaves like a distance function should, right? It behaves like every interaction we've had with distance behaves. So this is what we have. This is our desire here. And so how do I do this on a graph? In fact, there's a very natural way to do this on a graph. It is the way that, again, you might have thought about, right, before you knew anything about graphs. If you were just doodling on paper, this might have been the rule you came up with here. which is a distance. So distance in a graph G if U and V are vertices of G, the distance between U and V, we may, if we have multiple graphs we're considering, and we're considering distances separately in each graph, or if we have a graph that maybe has different components, we'll talk about that here in a second. Actually, let's go ahead and say, for now, distance in a connected graph G. This is not a big deal. You might think it is initially. You might think this is a big deal, but it's actually not a big deal at all, and we'll see how to ameliorate this for a generic graph. But distance in a connected graph G, where every UV is connected by a path. Remember, every UV is connected by a walk in a connected graph. And because of the second theorem of graph theory, that means that every vertex UV is connected by a path, okay, a UV path. So anyway, if we have multiple graphs showing up in some context, then we may label this in this fashion to make sure that it's clear we're talking about the distance in the graph G, right? Because we might also have showing up in the same place or similar place distance in a graph H. So that's to distinguish those things. But when the context makes it clear what graph we're talking to, we're just going to drop that and have this be d of uv. So d of uv, what is this? This is the length of a shortest uv path in G. And because of our previous work, the second theorem of graph theory, and all of that, we know that this is not ill-defined, right? This is a well-defined object. We can always come up with this length, so we denote it as d of uv, and let's do a quick example. So maybe I have let's just vertices here. Make these vertices bigger so you can actually see them. So let's label these. Let's say A, B, C, D, E, F, G, H, I, J, K, L, M, N. Okay. So there's our graph here. The question is, what is the distance from, say, B to K? So B to K, 1, 2, 3, 4. Was there a shorter way to get there, right? I could have gone 1, 2, 3, 4. That is the shortest way of getting there. There's no other way, right? I is not adjacent to K. If I was adjacent to K, of course, this would be 3, but as it stands, this is 4. What is the distance from, say, C to M? All right, so from here to here, 1, 2, 3, 4, 5, 6. Was there a shorter way to get there? 1, 2, 3, 4, 5, 6. Doesn't look like it, right? So 6. Okay. Distance from a vertex to itself is 0. Distance from, say, F to any vertex it is adjacent to is going to be what? Well, 1, right? So the distance from F to I is 1. It's going to be true for any vertex that it is adjacent to. So immediately this gives us another way of characterizing adjacency in terms of distance. Okay. So maybe it seems a little, you don't like the fact that I said here's a distance and now I'm talking about a length, but length is synonymous with distance. What do we mean by length here? Well, you saw what I did when I actually wrote this out, right? What is this? This is the number of edges in the shortest UV path, right? So when I mean length, I mean just the actual strict number of edges in the path. Okay. All right. So this is a powerful means to recharacterize a lot of things about graphs, and ultimately the goal here is to put the data we have about a graph into a form that is more amenable to computation. So the thing is that human brain loves looking at graph as picture because immediately there's a lot of things going on with how that is analyzed. But computer brain does not like looking at graph as picture. Even more sophisticated large language models and various other things are going to have a problem with necessarily with visual representations of graphs, especially when the vertex and edge count gets really large, right? Because remember, like omitting a single thing, omitting a single adjacency changes everything, right? So it is not one of these things that can be nicely smoothed out or averaged in the same way that identifying images, facial recognition, these things, there's some averaging process there that is present that is just simply not going to work here. Because if a single edge or vertex has anything about its adjacency change, that is it. It's over, right? It's a totally different graph. So naturally, what computer brain is going to be able to deal with much more nicely and cleanly is if we can take that data for a graph and put it into another form. Right? Ideally, you already know where this is going, right? This is if we can put it into the form of a matrix somehow, well, then computer brain is very, very happy with that. So that is much nicer for computer brain to deal with than a picture. So in this sense, let's start down this path. For a vertex, in the vertex set of some graph G, we'll say G is connected for now. As I said, we'll address the disconnected case here in a little bit. I want to define what is called the eccentricity of V. The eccentricity of V is the greatest distance from V to any other vertex. So this is written as ec V. This is defined to be the max over other vertices X in the vertex set of G of the set that is all the distances from V to those vertices. Okay. So, for instance, in this example, what is the eccentricity of A? Well, so I'm looking for the largest distance. So obviously C is distance 1 from A, B is distance 1 from A, but there are vertices that are clearly further. Let's try to see the furthest possible distance, right? So 1, 2, 3, 4, 5 if I go to N, K, or M. If I had went to H, 1, 2, 3, 4, oh, 1, 2, 3, 4. If I had went to J, I could go to G. Obviously, that's closer. So H and J, all these, everything here is closer to A than K, M, and N. L is the same distance away from A as H and J. So K, M, and N are the furthest from A, and 1, 2, 3, 4, 5. The eccentricity is 5. Now you might object and say, wow, if my graph was huge, this would be more annoying to compute. Yeah. But this is, again, consider what it is that's being done here and how, well, especially how this is going to fit together with how we kind of transform the way this data looks. Let's see here. Why is this distance defined as so? Question rather than minimum distance. How do you characterize different path lengths? So I'm gonna let's see. So if you mean the regular distance is defined as a minimum distance. It's the length of the shortest UV path. If you're talking about the eccentricity, we're going to have multiple things that we use the eccentricity to define. We are going to talk about like the smallest, largest distance from a particular vertex. The thing to focus on with eccentricity is that it is taking in as an argument a vertex, right? We are going to use that to label different properties that an entire graph can have rather than just something. So this is something that is particular to a vertex, right? I could choose vertices, other vertices where the eccentricity is, is going to be different. Like choose F, for instance, right? And consider the eccentricity of F. That's a good question here, just to practice here. Ponder what the eccentricity of F is. Okay, so now we're going to see how we can define this as, or how we can use this rather to define some other quantities in a graph that we're interested in. In this sense, right, I asked you to ponder the eccentricity of F. There are going to be vertices that have very small eccentricity. In fact, some of these vertices are going to have the smallest possible eccentricity for the graph. There are other vertices that are going to have the largest possible eccentricity. But in terms of how close they are to other vertices in the graphs, these are going to be special things, right? Special cases of vertices. So vertices that have the largest eccentricity are in some sense on like the outside of the graph, right? So think, in your mind intuitively, having a large eccentricity as a vertex means that you are very far from some vertices, which means you are like out there compared to those vertices. Okay? So you are on the outside or the periphery of the graph. Okay. Versus, well, what if you're like, what if you have the smallest possible eccentricity? What if you have an eccentricity that is as small as it can possibly be in your graph? What does that mean? Well, it means you're the furthest distance for you is much smaller than some other vertices might have. You are in the middle, right? You're like in the center of the graph. You're right in the midst of things. You are closer to everything than vertices with a large eccentricity. So this eccentricity defined as the largest distance is the thing that tells you these things, right? It tells us that and of course if we had defined it as the smallest, the things I just said would be the opposite, which intuitively would not make as much sense to us. That's like an extra step we would have to basically invert in our brains. So that's why we used largest distance here instead of smallest. It just meshes with how we have defined this and being closer versus further away, right? Those closer and further would basically be inverted if we'd use smallest. So instead of largest. How can we define? I want to define all of the terms related to eccentricity here. So here's some definitions. The radius of right now again a connected graph G, but we're going to see how to apply this to any graph. The radius of G is the value of the smallest eccentricity of G. So it's defined as the radius of G. This is the smallest eccentricity. Of a vertex in G. Precisely, of course, we could write this as this is the min over vertices in the vertex set of G of the eccentricity of V. So this is the smallest thing. Okay. The diameter is the value of the greatest eccentricity. This is the greatest eccentricity. So I'm not going to rewrite the statement in words. I'm just going to write it as this. It's the max of these eccentricities. Okay. Now, those things that I said before, those words, center and periphery, right? That is the inside and the outside, right? The center of a graph G is the set of vertices V satisfying that the eccentricity of V is actually equal to the radius of G. So I'm not going to write that in set builder notation, but it's just the set of, okay, maybe I should. So the center of G is the set of all vertices in the vertex set of G such that the eccentricity of V is equal to the radius of G. The periphery of G is the set of vertices equal to whose eccentricities are equal to the diameter. So the eccentricity of V is equal to the diameter of G. So I'll write it in set builder notation just to do it, just for completion's sake. So it's the set of vertices such that the eccentricities are equal to the diameter. So another way to rephrase this in words, right? The center of G is the set of all vertices that have the smallest possible eccentricity, and the periphery is the set of vertices that have the largest possible eccentricity. So the center is the set of vertices that are the closest to all vertices, and the periphery is the set of vertices that are the furthest from all vertices. Phrased in that way, right, all of this intuitively at least matches and makes sense. Okay. So let us go back to our picture. In this, what is the radius? If this is G, what is the radius? What is the smallest possible eccentricity? Well, turns out the smallest possible eccentricity is actually here at F, also at E, also at G. The eccentricity of F, if you were thinking about it, what is it? You can tell me in the chat. I'll believe you, even though by the time it types, I will have revealed it. This is 3. The eccentricity of E is also 3. The eccentricity of G is also 3. Okay. So, can I get a smaller eccentricity than this? No, I can't. And I'll leave it to you to try to investigate some of these other vertices that you think might have smaller eccentricities, but like B, for instance, does not have eccentricity 3, it has eccentricity 4. Okay, so I is the same way because it's distance, so the distance from I to C, for instance, is 4. So the radius here is 3. This is the smallest eccentricity that we get. What is the diameter? So we already have seen that A has eccentricity 5, but are there any vertices that have eccentricity greater than A? Well, are there... What's kind of a way of thinking about this, right? Like, how would I increase my eccentricity? I would take A. I know it has eccentricity 5. Now I'm looking for a vertex that A is adjacent to that is even further away from other vertices. Do you see such a thing? C. Right? C. It's the only other vertex that A is adjacent to, right, other than B. C. What is the distance from C to N? 1, 2, 3, 4, 5, 6. How about from C to N some other way? 1, 2, 3, 4, 5, 6. 6. Does it get larger than that? What about the distance from N to, well, we know the distance from N to C is 6. What about K? What's the distance from K to C? 1, 2, 3, 4, 5, 6. Also 6. M. Also 6. The diameter of G is 6. This is the largest that we can make our eccentricity here. And the process of doing that, we actually found the vertices that make this eccentricity as large or as small as I need, or as small as it can be, right? So what are the set of vertices that have eccentricity 3? So what are the set of vertices that have eccentricity equal to the radius of the graph? Well, E, F, and G. Those are the only ones. So the center of our graph G in this example consists of the vertices E, F, and G. Those are the center. But what about the periphery? What is the periphery? So the periphery of G consists of all those vertices that have the largest possible eccentricity. Right? Their eccentricity is equal to the diameter, which is 6. We saw that C has eccentricity 6. So does K, N, and M. So C, K, M, N. Form the periphery. And now it's clear intuitively what is being discussed, right? What is being like singled out by these things. The center, right? These vertices. Hey, that's like the middle of the graph, right? It truly is like the center of the graph. It's the vertices that are as close as possible as they can be to all other vertices. And the periphery consists of those vertices, which are the furthest they can possibly be from all other vertices. Okay? That's the periphery. That's the outside. The center is the inside. Okay? Well, you might already be thinking, well, we've used a lot of terminology here, right? Radius, diameter. That might get you thinking that there's a huge analogy to be had with circles or circular disks. And that's true to some extent. It's not like a 100% perfect analogy, but a good way of understanding it is the following theorem. So for any connected graph, the radius of G is necessarily less than or equal to its diameter, although these could be equal. In fact, before I prove this, I'm going to think about where these can be equal. And this itself is less than or equal to 2 times the radius. So here are bounds for both the radius and the diameter here. So I'm going to prove this. This is a short proof here in a second. But before I do, I want to think about what it means if the radius and diameter are equal. So I'm including that as a possibility in the statement of this theorem. But why? Why is this not strict? Let's consider a quick example. We're talking about distances which, are related to questions of adjacency, obviously. Talking about distance, let's just go to our extreme cases immediately, right? So let's consider a cycle or a complete graph. So in a cycle, So here's C8. A complete graph, I'm not even going to draw it, even for a small one. We're just going to think about it. But for this cycle, um, what is the eccentricity of this thing right here? All right, so this vertex. What's its eccentricity? Hmm. Well, its shortest path is the distance. So, for instance, going all the way around, well, there's a shorter way to do that. Well, let's see here. 1, 2, 3, 4. That's the shortest distance to here. 1, 2, 3, 4. That's the only way to get there. But each of these is going to have the same this same eccentricity, right? 4 is the furthest away vertex for this one. Each of these is going to have that same issue, right? Each of these is going to behave in exactly the same way. So for every vertex, its eccentricity is going to be exactly equal. So if these vertices are labeled VI, right? V1, V2, and so on. The point is that the eccentricities of VI and VJ are equal, right? I and Y. So all the eccentricities are equal. What about the complete graph? What's the eccentricity of any vertex in a complete graph? Someone tell me what the eccentricity is of a vertex in a complete graph. What is the let's remember what eccentricity is. What is the largest distance from any vertex in a complete graph to any other vertex? Well, in a complete graph, any two vertices are adjacent, right? So the distance from any vertex to any other vertex is 1. Yeah, it's just 1. Whoop, put my So, in the same way, all these eccentricities are equal. They're actually equal to the same number. So, and this is also true for a cycle. They're just equal to the same thing. And so, in both of these cases, the radius is equal to the diameter. And so this is something you have to keep in mind. Obviously, this again goes into what I was saying yesterday, which is whenever you encounter something, the first thing you can ask yourself is, okay, how does it apply to the empty graph? Maybe that's too simple. How does it apply to complete graphs, cycles, paths? Right? You use your special types of graphs to see how the thing applies to those, how the statement applies to those things. Okay. So let's go back and prove this this bound. Okay, so by definition, because radius is the smallest eccentricity and diameter is the largest eccentricity, right? So this is the min and this is the max. By definition, this part is satisfied. But we did have to show that they can be equal. Okay. Again, from the fact that they're equal, you see that all those eccentricities have to be equal. But okay, by definition, the radius of the graph is less than or equal to the diameter of the graph. So all I need to prove is the second part. Thus, let U and V be vertices in G such that the distance from U to V is equal to the diameter of G. Such vertices have to exist by definition of what the diameter is, so we've just picked two vertices such that their distance is the diameter. Okay, so we can always do that. Let C be a vertex in the center of G. Again, that always exists, right? Maybe the center is the periphery, right, in these extreme cases, but nevertheless, the center exists. I can pick a vertex in it. Okay, so let C be a vertex in the center of G. Then what do we get? The diameter of G is this distance from U to V. Where does the C come in? You know where it comes in. The triangle inequality. The favorite tool of all mathematical tricksters when it comes to, using triangle inequality as a trick to get the bounds that you want in some proof. Now, because C is a vertex in the center, the distance from vertex U to C cannot be more than the eccentricity of C, right? That is the definition of eccentricity. Eccentricity is the largest such distance. So this is less than or equal to the eccentricity of C plus the eccentricity of C because the eccentricity is the largest of all such distances from some other vertex to C, from C to some other vertex. But this is 2 times the eccentricity of C. But the eccentricity of C, because it's in the center, is what? The radius. And that's it. Okay. So that's that. This is a nice bound in this way. Now, I've kept ever since the first class today saying that I was going to show that requiring the graph be connected is not that big of a deal. And that might seem surprising to you at first because you're like, wait, if it's not connected, then like, how do you even talk about the distance between pieces that are disconnected in disconnected parts of the graph? So here's how. It turns out, I want to make sure I'm saying this isn't necessarily related to this. It turns out that if G is disconnected, we can still talk about distance in almost the same way. Could still use all this distance stuff. How? Well, if the vertices in question are in a single connected component, of a disconnected graph, then nothing changes, right? If the vertices in question lie in the same connected component of G, nothing changes. Right? Because that component is itself connected. So if all the vertices I'm taking are only in one connected component, I'm fine. So then the only difficulty or potential difficulty arises when you have vertices in differing connected components, right? So if two vertices are in different connected components, what do? You just say that the difference between them is infinite. This respects all of the rules of this thing being a metric. Our distance function still works perfectly, and even intuitively, this makes sense to us because if a graph is truly disconnected, then vertices in different components have infinite distance to one another because you can't get from one to the other, right? There is not a UV path that takes you from one to the other, so their distance is infinite, right? It is impossible to get there. So this works just fine. But typically, the way that this is handled is right. You say, well, if they're different, if they're in different connected components, the distance is infinite. So suppose that we're working in the same connected component, but now you're just in the connected case. So everything proceeds as it normally does. So I mentioned yesterday that the first time we mentioned subgraphs, that talking about sub things in a field, this is always an important part of any field of study once you talk about substructures, right? So subgroups in algebra, of submanifolds in differential geometry. Whenever you're talking about sub things and how they're related, that's where you're really getting into the meat of what is important. And many of those questions are very, very hard. But here, I'm more asking, these centers and peripheries, are they special? Do they look special? Or are they special in some way? And the answer is not really. Okay. So the first theorem I have that shows this is the statement that every graph is isomorphic to the center of some graph. Now, this is isomorphic to. We can replace that with the word is if you like, if you want to read this in a snappier fashion. That's not going to cause us any philosophical problems. Every graph is the center of some graph. Okay. So every graph contains, or every graph is contained as, as the center and a subgraph of some other graph. How would you prove this? I mostly wanted to talk about this theorem for the proof technique, which is something that is not entirely unique to graph theory, but it is a very nice feature of graph theory that you often have proofs like this that are extremely intuitive and mostly visual. So let G be your favorite graph. All right, all of you already have a favorite graph by now, I'm sure. So let G be your favorite graph, whatever it is. Okay. Now, I construct a new graph H, which has G as its center. How do I do this? I do this by adding 4 vertices. We'll call them W, X, Y, Z in this way. So, what I do is I have the graph G, whatever it is. There's your graph G. Then what I do is I take a vertex that I'll call X and another vertex that I call Y, and I connect X to every vertex in G. I take Y and I also connect it to every vertex in G. Then I connect X to a single other vertex W. I take Y and connect it to a single other vertex Z. Now, I claim that I have constructed a graph of which G is the center. So maybe you're worried about this. Maybe you're extremely worried that this picture, you somehow have a problem translating it to math. So you're worried that this isn't exactly rigorous. But it is. So what is it that I do here? All I do is that I add 4 vertices to G. So I add 4 vertices to G along with the edges. So like, what does this picture say? I'm adding the vertices W, X, Y, Z to G. With edges, I'm adding the edge WX and YZ. Those 2 edges get added. Also, every edge connecting X to a vertex in G. So this is the collection of edges that look like XU, such that U is a vertex in G. And then I union that with the collection of every edge, say YV, where V is a vertex in G. And that's it. So that line, right, mathematically is exactly what this picture is representing here. And now let's check. Let's quickly check here. Well, what is the eccentricity of W? What's the largest possible distance from W to another vertex in this graph? So here's my graph H, right? So W can be connected to X in one step, right? That's 1. Then W can be connected to any vertex in G in 2 steps. That is, you go to X and then you go to any vertex you want. From any vertex in G, it can get to Y in 3 steps, so its distance to Y is 3. Its distance to Z is 4, because this is the only last thing to do here. So the eccentricity of W is 4. Similarly, the eccentricity of Z is 4. The eccentricity of X is 3, because X can go to W in 1 step. X can go to any vertex in G in 1 step. X can go to Y in 2 steps. X can go to Z in 3 steps. That's it. 3 is the only thing here. And similarly, the eccentricity of Y is also 3. But if a vertex V is in the vertex set of G, what is the eccentricity of that vertex V? What is its largest distance? So it's in G. It can go to any other vertex in G, even if G did not have the adjacency that you think, right? So even if in G itself it took you 100, it was distance 100, but from some vertex to another vertex. Because I've added in these edges, I can go from any vertex in G to any other vertex in G in distance 2. I go out to either Y or X, and then I go back to whatever vertex I want in G, because both X and Y are connected to they're adjacent to every single vertex in G. So if I'm in G, I can get to any other vertex in G in 2 steps, 1, 2, or 1, 2. What about going to Z? I go out to Y and then to Z. What about going to W? I go out to X and then to W. X and Y are both adjacent to every vertex in G. What's the largest possible distance? 2. Which is the smallest eccentricity on this list. Any vertex in G has eccentricity 2, according to this. That's the smallest eccentricity on this list. This exhausts all of the vertices in the graph H, and so G, and exactly G, nothing else, right? The eccentricity of X and Y are both 3, eccentricity of W and Z are both 4, so the only vertices that get included as having eccentricity 2 are exactly the vertices of G, so G is the center of H. And that sort of proof is a very, very nice thing that we can do sometimes, right? Sometimes we are stuck in more traditional sorts of proofs where, it's some hard induction step and we've got to really go through things. But oftentimes we are left with, being guided by this sort of thing. And, well, I'm going to say we're always guided by this sort of thing typically, but sometimes it's a little bit more powerful. There's another theorem that I'm not going to prove. I will tell you where the proof is, however, which also says a similar analogous thing except for the periphery. So a graph G is isomorphic to the periphery of some graph if and only if the following. So a graph G is isomorphic to the periphery of some graph if and only if either every vertex has eccentricity 1 or no vertex has eccentricity 1. You might think for a second why this is true. Of course, if we start with the backwards implication, if every vertex has eccentricity 1, it's a complete graph, right? So that actually works because the complete graph is the periphery of itself, right? So so that part is instant. Okay, the other one is what if no vertex has eccentricity 1? So that's where I will stop and let you consider it. So first, the idea, this is the backwards implication. If every vertex has eccentricity equal to 1, it is complete. Thus is its own periphery. If no vertex has eccentricity 1, then you have to think a little bit more, and then we'll do the other direction. So, or then you can look at the other direction as well. Fill in the blanks here. This is on page 20 of the textbook, if you want to have a look at the reasoning there. Okay. Okay. So, next, I'm going to introduce this. We're going to talk about it for a few minutes, and then that will be all for lecture today. Matrices and graphs. So as I hinted earlier, right, there's certain niceness to a picture, right, to a visual representation of a graph, as we've been seeing in this course. Certain niceness that the human brain really likes, and it's encoding a lot of information. Of course, the human brain is going to have problems with pictures that involve a lot of vertices, but even so, human mind is able to deal with those sorts of things in a way that's a little bit more straightforward than computer mind deals with it. The computer mind much would prefer having a matrix if possible, right? Because that is exactly what computer is the absolute best at dealing with. And then you don't have to worry about, oh, did the large language model I'm using miss one of the vertices when it was translating the picture, right? In which case everything that follows is garbage. That is not possible when you have the thing encoded as a matrix. Because that would be missing an entry in a matrix, or having an entry wrong in a matrix, and that's the entire point of making this more amenable to computation. So on the other hand, linear algebra, right? The joke usually is that linear algebra is the only field of math in which everything is understood. That's not actually that far from accurate. The main point of this really is to say that whenever you have a problem of almost any kind that you're dealing with mathematically, or in any kind of related thing, whether it's applied math, physics, whatever you're dealing with, CS, if you can take the problem that you're having and translate it into a problem involving vector spaces and linear algebra, you are very happy to do that. Typically, it is much easier to deal with a problem in the world of linear algebra than it is in whatever world it came from. Okay, that is almost always true. So you're typically very happy when you can do that. And so I'm going to define the following. Let G be a graph with vertices v1 to vn. So it's a graph of order n. Okay. The adjacency matrix of G is the n by n matrix A whose ijth entry that is the entry in the ith row jth column. We are going to denote this just to follow the textbook, the way the notation is used in the textbook. I'm going to keep this notation the same, even if maybe this is a little bit more cumbersome than what you would see in linear algebra. It's denoted by a ij, multi-index like that. Okay, is defined by the following. So its ijth entry, that is the entry in the ith row, jth column, is 1 if vi and vj are adjacent, and 0 otherwise. Most computer-friendly thing possible, right? Okay. So let us draw a quick example course. So we have, I'll label them clockwise here. This is V1, V2, V3, V4, V5, and V6. This is our graph G. What would the adjacency matrix A look like for this thing? So this is going to be a 6 by 6 matrix. So in the first row, right, the first row is going to be corresponding to this first vertex. I'm basically going to be tracking the vertices that it is adjacent to. It is adjacent to vertices 4 and 5. So this corresponds to having 1s in the 4th and 5th column. So this would be 0, 0, 0, 1, 1, 0 would be the first row. The second row is tracking the adjacency of vertex 2. It is only adjacent to vertex 3, so it's going to be a row of nothing but zeros, but 1 in the third column. Third row tracks the adjacency of vertex 3. So vertex 3 is adjacent to both vertices 2 and 6, so this is 0 everywhere except in the second and 6th column. Similarly, vertex 4 is adjacent to vertices 1 and 5, so this is a 1 in the first column, and then in the 5th column is another 1. 5 is adjacent to vertices 1, 4, and 6, so I have another 1 in the first column, and then a 1 in the 4th column, and a 1 in the 6th column. And then lastly, vertex 6 is adjacent here to, yeah, that's fine. I was copying the example from the textbook, but I realized that I left out an edge, but that's perfectly fine here. So this is going to differ from the example on page 22. So different from page 22. But that's actually good. So now you get 2 examples instead of 1. So then the 6th, this is adjacent to vertex 3 and 5. So this is, I'm going to have a 0 everywhere except the 3rd column and the 5th column. Okay. That's what the adjacency matrix looks like. A few things to notice. Since a vertex is not adjacent to itself unless we allow loops, for these simple graphs, the diagonal of A is zeros. because the only way there'd be a 1 there is if a vertex was allowed to be adjacent to itself via a loop, which we're not allowing if this is a finite simple graph. And so that's one thing to notice. The other thing, adjacency is symmetric. What does that mean for the type of matrix this is? This is a symmetric matrix. Okay. Now, this business here, is this always the case? Think of a special case where this wouldn't work. So think of when this isn't true. Note, this is true for our finite simple graphs as we're considering them, but think about where this isn't true. Go back to the first day of class. We're talking about all the different types of graphs that are not necessarily finite simple graphs, and think about when this isn't true. Okay? So, but for us in these sorts of graphs, this is absolutely going to be the case, and so this is going to be a symmetric matrix. What is nice about having a symmetric matrix? Remember, what does a symmetric matrix mean? It means swapping the rows and columns has no impact. The matrix is equal to its own transpose. Being a symmetric matrix with not just real entries, but also integer entries, non-negative integer entries, is that means your matrix is basically as nice as possible. The very end of Math 240, Math 461, if you took those courses at UMD, you discuss the consequences of dealing with a symmetric matrix, and they are very, very nice. Symmetric matrices, for instance, that have real entries are guaranteed to have distinct real eigenvalues, for instance, which means they are diagonalizable, right? So these are basically as nice as possible. In terms of diagonalizability, for instance, having symmetric matrices is really, really nice. But anyway, so that is essentially guaranteed. Although, as I said, go back to the first day of class and think of some of those other special types of graphs and when adjacency would not necessarily be symmetric. Okay. What about a directed graph? What about a digraph? Right. That's the hint. Anyway. Okay. So that is that. I think I'm almost exactly, we're like 20-ish minutes over as the plan. Tomorrow again the lecture will be approximately 20 minutes longer than is typical, and then next week we'll be back to the normal hour and 20-minute lectures. We won't have to make up any more time from the document cam exploding on the first day. So anyway. That's all for today. I'm going to post your homework a little bit later today, like in a few hours. We'll say don't worry about it. It'll be due Monday evening, Monday night. When I post it, I will make an announcement to Elm, so you don't have to be sitting around waiting. You'll get the notification when I post it. It will involve some problems from a few sources. So textbook mostly is where most of the problems come from. But I might ask you some other things as well. But anyway, for this first homework set, it's mostly going to be textbook problems. So anyway, that is that. I will see you all tomorrow.